Welcome to the deep dive. We got this paper, a language for large-scale collaboration in economics. And, well, it's got us thinking. It's about a new way of looking at financial models, this thing they call computational representations.
Yes, this paper, it's tackling a big challenge we have in economics. How can we, make research more open, make it reproducible, easier to collaborate on? It's like they're trying to, I don't know, create a universal language for economists, you know, to share their ideas and data and everything.
So it's not just the numbers themselves. It's like making a system where everyone can understand and build on each other's work, right?
Yeah.
What exactly AX, a computational representation? It sounds kind of intimidating.
It's not like a specific programming language or anything, it's more like a framework. Imagine, like a set of building blocks that everyone agrees on, a way to define those economic concepts so computers can understand them, share them.
Okay, I think I'm starting to get it. But why does why does it need this so badly? What's the problem we're trying to solve?
Well, economics is facing what some call an informatics crisis. We have mountains of data, but it's often siloed, difficult to interpret, even harder to replicate. Imagine trying to understand a financial model that's it's locked away in someone else's code. It's like trying to solve a puzzle with half the pieces missing.
And that's where this paper comes in, right? They're proposing a solution, a specific computational representation called sigma. And from what I'm reading, it sounds almost like, I don't know, a specialized Lego set for economics.
That's a great analogy. Sigma, it's built on a few key ideas. They call them facets, contributions, and constraints of data. Kind of like, the rules and pieces that make up this whole economic Lego system.
Right. This is where things get interesting for me. Let's break those down. What are these facets all about?
The paper, it highlights four main facets: streaming, reactives, distribution, and simulation. Think of them as like the core principles, the things that make Sigma work.
Okay, streaming. That one sounds familiar. Is that about, handling the constant flow of information, especially, in the financial markets?
Exactly. It's about processing data in real time as it comes in. Think of it like analyzing stock prices tick by tick, making decisions on the fly based on the, latest market movements and all that.
That makes sense. For someone like you constantly tracking all that financial data, streaming seems pretty crucial. But what about reactives? That one sounds a bit more mysterious.
Reactives, they introduce a really powerful concept here. Imagine a spreadsheet, right? And when you change one cell, it automatically updates all the related formulas. So it's not about like step-by-step instructions. It's about defining those relationships between data points and letting the system, figure out the rest.
So if one variable changes, the whole system adjusts accordingly. That sounds incredibly efficient, but also could it be risky? I mean, what if one data point is wrong?
That's a great question. And it highlights the importance of, data integrity, data validation, all that. But when done correctly, this reactive approach can make models much more flexible, more adaptable to, real-world changes.
I see how that could be, really a game changer for economic modeling. We've covered streaming and reactives. What about distribution? Does that relate to, I don't know, the sheer volume of data that economists work with?
You're on the right track. Distribution, it's all about breaking down complex models into smaller chunks that can be processed in parallel, like, splitting a giant research project into like manageable tasks for different teams to work on at the same time.
So it's about leveraging all that, computing power to tackle those massive data sets
Yeah.
to speed up the whole process, right? Makes a lot of sense when we're talking about, analyzing global economic trends or building those huge simulations. Okay, that leaves us with simulation. Seems like simulations are at the heart of a lot of economic research. How does Sigma handle that?
Simulation is absolutely essential in economics, and Sigma offers a really flexible approach. You can create virtual environments and test different hypotheses. It's kind of like running a controlled experiment, but in a computer. Could be anything from, I don't know, predicting stock prices to understanding how people react to new policies, all sorts of things.
So with Sigma, we're not just analyzing the past, we're actually building models to explore those future possibilities, the what-if scenarios.
Exactly. And what's fascinating is how these four facets, they all work together. They create a really powerful system, for handling data, building models, exploring those complex economic questions.
This is all pretty mind-blowing. We've covered the facets, those foundational principles of Sigma. Let's move on to the next piece of this economic Lego set, the contributions. What exactly are we contributing here?
Think of these as the Lego bricks themselves, the building blocks of our models. The paper divides them into three main types: financial models, processors, and endpoints.
All right, let's unpack that. Starting with financial models. What exactly do they represent in the context of Sigma?
In this system, a financial model is like a blueprint for a specific economic process. It lays out the steps, the calculations, the data needed to represent, I don't know, something like a pricing model, a risk assessment, or even a whole market simulation.
So, if the facets are the rules of the game, financial models are the strategies we create using those rules.
Precisely. And just like a good strategy, a financial model built with Sigma, it should be clear, concise and easy to understand, even for someone who, didn't create it.
Okay, that makes sense. What about processors? Are those like the individual actions or calculations within a financial model?
Exactly. Think of them as the verbs in our, economic language. They're the workhorses, they take in data, they perform calculations, they produce outputs.
So a processor could be something like calculating a moving average, running a regression analysis,
Yeah.
or even generating a, I don't know, buy or sell signal based on certain market conditions.
You got it. Here's where things get really exciting. The vision for Sigma is to have a library of pre-built processors that, anyone can use, need to calculate a specific financial ratio. There's a processor for that. Need to model a particular type of market behavior. There's a processor for that too.
Wait, so instead of reinventing the wheel every time,
hmm
we could have this massive toolbox of ready-made components that we can, plug and play into our financial models. That sounds incredible. What about these endpoints? Where do they fit into all of this?
Endpoints, they're the sources and destinations of data in our system. Think databases, real-time data feeds, visualization tools, or even other financial models. They're how we connect our models to the real world, whether we're pulling in data, displaying results, or interacting with other systems.
So it's like the inputs and outputs of our, economic Lego creation. We've got the building blocks, the financial models. We got the actions, the processors, and the connections to the outside world, the endpoints. I'm really starting to see how this all fits together. And the collaborative potential here is huge, right? It's like building a giant economic Wikipedia where everyone can contribute, everyone can learn from each other.
Exactly. It's about democratizing access to knowledge and tools, breaking down those silos that often exist in research.
Okay, we've explored the facets and the contributions.
Yeah.
What about that final piece of the puzzle? The constraints of data. It sounds a bit like, well, limitations.
Think of constraints of data, less like limitations and more like, I don't know, the instruction manual for our Lego set. Make sure we're building things correctly, make sure all the pieces fit together as intended. They ensure consistency, they prevent us from creating, nonsensical models.
So it's about establishing rules and guidelines to maintain the integrity, the reliability of the whole system.
You nailed it. The paper, it highlights three main types of constraints: configuration, execution, and simulation.
Okay, I'm all ears. Let's dive into those. What exactly are configuration constraints all about?
Configuration constraints, they're all about documenting the structure and connections within our financial model. It's like taking a snapshot of your Lego creation so you can remember, how you built it, replicate it later if needed.
So it's about capturing the exact arrangement of those processors, the endpoints, the relationships, all at a specific point in time. And since models can change over time, having these configuration snapshots helps us track those changes, understand different versions, ensure everything is, reproducible. What about execution constraints?
Execution constraints are all about defining the type of data that flows through our model and how it's, transformed at each step. It's
Yeah.
about ensuring those calculations make sense, making sure that we're not, mixing apples and oranges.
So if a processor expects, let's say, stock prices as input, an execution constraint would prevent us from accidentally feeding it something like, I don't know, weather data. It's all about maintaining data integrity and, preventing errors. That makes perfect sense. What about simulation constraints? Those sound intriguing.
Simulation constraints are specifically for, well, simulations. And as we discussed earlier, simulations are, incredibly important in economics. They can involve a lot of assumptions, a lot of parameters.
Hmm.
So we need to make sure those are clearly defined and consistent with the goals of the simulation.
It's like setting the stage, establishing the rules of the game for our simulation. We want to make sure it's a fair and meaningful representation of the real world scenario we're trying to, study.
That's a great way to put it. These constraints, whether they're related to configuration, execution, or simulation, they're crucial for building, robust, reliable financial models.
Okay, so we've explored the facets and contributions of Sigma, and now we've got a good handle on the constraints of data as well.
I'm really starting to see the potential here. It's a bold idea, right? It has the potential to revolutionize how economists work, how they collaborate, but it's a lot to take in. Where do we go from here?
We've only scratched the surface. There's so much more to explore in this paper, from specific examples of how Sigma can be implemented to the potential benefits, the potential challenges it presents. And that's what we'll dive into next. When I first started reading this paper, the concept of streaming really stood out to me. They actually use something called Petri nets to visually represent how streams work. Petri nets, okay, that rings a bell vaguely. It was probably buried somewhere in my college computer science notes. Remind me what those are all about.
Imagine like a network of circles and squares connected by arrows. The circles, they represent places where data can, reside, and the squares represent transitions that process or modify that data. It's a visual way to model how data flows through a system.
Okay, so data moves through this network from one place to the next, getting processed along the way. It's like an assembly line, but for information instead of car parts.
Exactly. And the arrows, they show the direction of the data flow. A transition, it can only happen if all the connected places have the, necessary data. It ensures that everything happens in the right order, nothing gets lost, and the process, keeps moving smoothly.
So it's a way to visually map out a complex process step by step. I'm starting to see how this connects to streams in Sigma. Can you walk me through that?
Think of a stream in Sigma as like a chain of processors working together to handle that constant influx of data. Each processor is like a transition in the Petri net, and the data flowing between them, it's represented by those places. It's a powerful way to visualize and understand how that data is being processed, within a financial model.
Okay, so we're essentially mapping those processors in our Sigma stream onto this visual representation of a Petri net. And this isn't the only way to represent streams, right? The paper mentioned other models of computation as well.
You're absolutely right. Sigma provides the framework, those big picture concepts, but it doesn't, dictate the exact method of implementation. This allows for flexibility and innovation. Researchers can choose the approach that works best for them for their specific needs.
So there's room for different perspectives and approaches, which makes sense in a collaborative field like economics. We've seen how Petri nets can represent streams. What about those other, fascinating facets? Does the paper give any real-world examples of how those could be implemented?
Absolutely. They dive into reactives using the example of an electronic spreadsheet. You know how you can define relationships between cells, using formulas?
Oh, yeah, like if you change the value in one cell, any cells that depend on it, automatically updates, like a domino effect, but with numbers.
That's a perfect way to think about it. And that's the core idea behind, reactives. Instead of writing code that tells the computer exactly what to do at each step, you define these relationships between data points and let the system, handle the updates. It's a much more efficient way to manage complex models.
So it's less about giving specific instructions and more about setting up this, I don't know, this dynamic web of connections. And the system is smart enough to figure out the rest. But wouldn't that level of automation be risky? I mean, could it lead to errors cascading through the system?
That's a valid concern, and it's why testing and validation are so important. But when implemented correctly, this reactive approach can make models much more flexible, much more adaptable. Imagine a financial model that can instantly adjust to changes in, market conditions or new economic data. It would be a powerful tool for, analysts, policymakers, all sorts of people.
Okay, I could definitely see the potential there. We've covered streaming and reactives, both dealing with the flow, the interconnectedness of data. What about distribution? How did the paper bring that concept to life?
Remember our analogy of splitting a giant pizza into slices? It's about dividing that workload to make things more manageable, more efficient. The paper uses the concept of spaces to illustrate distribution. Imagine breaking down a complex financial model into smaller, self-contained units that can be processed independently.
So each space is like a mini model running on its own, focusing on a specific part of the overall picture. And they all communicate with each other to, produce that final result, kind of like a team of specialists working together on a big project.
Exactly. Each space can run on a separate computer
Oh.
or even in a different location, allowing us to take advantage of distributed computing power. Is how we tackle those, massive data sets that are so common in economics, like, trying to analyze global trade patterns or simulating the behavior of entire financial markets.
It's like having a supercomputer at your fingertips. Okay, that leaves us with simulation, which seems, crucial for understanding those complex economic scenarios. How did the paper approach the topic of simulation within Sigma?
They actually present a whole taxonomy of simulation techniques, breaking down the different approaches based on, factors like time, randomness, data organization, all sorts of things.
Okay, a taxonomy of simulations. That sounds intriguing. I'm all about, categorizing things. Can you give me a quick overview of those categories?
They start by distinguishing between static and dynamic simulations. A static simulation, it captures a single point in time, like a snapshot. While a dynamic simulation, it models how a system changes over time.
So a static simulation might be used to analyze, let's say, a company's financials on a particular date, while a dynamic simulation could model how that company might perform over the next, I don't know, 5 years,
Yeah.
taking into account various factors like market trends, economic conditions, things like that.
Exactly. And then they break down dynamic simulations further into, time-stepped and event-driven models.
Huh.
A time-stepped simulation, it moves forward in fixed intervals like days or hours, while an event-driven simulation jumps from one significant event to the next.
Interesting. So a time-step simulation might be used to model population growth, over decades, while an event-driven simulation might be better for analyzing something like stock market fluctuations, where major events can trigger sudden shifts in price.
You getting it. And they go on to distinguish between deterministic and stochastic simulations. A deterministic simulation always produces the same results, given the same inputs, while a stochastic simulation incorporates randomness.
So a deterministic simulation might be used to model a simple interest calculation, while a stochastic simulation would be needed for something like weather forecasting,
Mhm.
where unpredictable factors play a huge role.
Precisely. And finally, they discuss different ways to organize data within a simulation, like using grids or, mesh-free approaches. The point is that Sigma is flexible enough to accommodate a wide range of simulation techniques. Researchers, they aren't limited to one specific approach.
This taxonomy is really helpful. It shows how much thought has gone into designing Sigma. It's not just about throwing together some code. It's about creating a system that can handle the nuances, the complexities of economic modeling and simulation. We've covered a lot of ground here. We've looked at how streams can be represented visually using Petri nets. We've explored real-world examples of reactives and distribution and delved into those different types of simulations Sigma can handle. What's next?
Now that we've got a grasp on the four facets of Sigma and, how they work, let's bring it back to those contributions we talked about earlier. Those building blocks, financial models, processors, endpoints. How do they all fit into this framework?
All right, back to those contributions. We've got these building blocks, financial models, processors, and endpoints, all working within that framework of Sigma's four facets. It's a lot to keep track of. How do those contributions come into play when we're actually building something in Sigma?
Think of it like this. You're an economist and you want to build a model to, I don't know, analyze risk in a portfolio. Using Sigma, you could start by selecting a pre-built financial model for, portfolio risk assessment from that shared library we talked about.
So instead of starting from scratch, we're drawing on this shared pool of, knowledge and resources. That's a huge time saver right there.
Exactly. Then you can start adding in your own, custom processors. Maybe you have a unique algorithm for calculating a specific risk metric, or perhaps you want to integrate data from a, particular market feed.
So we're taking those, pre-built components and tailoring them to our specific needs. It's like, I don't know, customizing a car. You start with a solid foundation and then add those features that are, important to you.
That's a great way to think about it. And of course, you'll need to define your endpoints. Where's your data coming from? How do you want to visualize or share the results? Sigma gives you the tools to connect your model to the real world, whether it's pulling in data from a database or, I don't know, displaying those results in a dynamic chart.
So we're combining pre-built components with our own, custom elements, all within this framework of Sigma's facets. It's powerful stuff. But we haven't talked much about those constraints of data,
Mhm.
configuration, execution, simulation. How do they come into play when we're actually building and, using these models?
Mhm. They're essential for ensuring that our models are, robust, reliable, and that they make sense. Remember, those constraints are like the instruction manual for our economic Lego set.
Right. They make sure we're building things correctly, not
Yeah.
creating something that falls apart the moment we touch it.
Exactly. Let's say you're building that portfolio risk model. A configuration constraint might specify that you need to include certain types of data, like historical stock prices,
Mhm.
interest rates, and currency exchange rates. This makes sure you're not, missing any crucial pieces of the puzzle.
Okay, so it's like a checklist, ensuring that we have all the necessary ingredients before we start, I don't know, baking a cake. What about execution constraints? How do those work in practice?
An execution constraint might dictate the order in which certain calculations need to happen. Maybe you need to calculate the portfolio's, overall value before you can assess its risk relative to a benchmark.
So it's about ensuring a logical flow of operations, kind of like a recipe that tells you to mix the dry ingredients before adding the, wet ones. And what about simulation constraints? Those sound particularly important when we're dealing with, complex economic scenarios.
Think of simulation constraints as setting the ground rules for your virtual experiment.
Hmm.
If you're simulating, let's say, a stock market, you might set constraints on the trading rules, the number of participants, or, I don't know, the range of price fluctuations allowed.
So it's about creating a controlled environment for your, simulation, making sure it's a fair and realistic representation of that real-world scenario you're trying to, study. And here's a thought that just occurred to me. Could these constraints also be shared and reused, just like the financial models, the processors, the endpoints?
That's a fantastic point. And yes, that's part of the vision for Sigma. Imagine a library of pre-built constraints that you could just, I don't know, incorporate into your own models.
Yeah.
It would save researchers a ton of, time and effort and help ensure consistency across different studies.
Wow, that's a powerful idea. It's like having a whole toolkit of, pre-tested and validated methods at your disposal. It would really raise the bar for, economic research.
Exactly. And it's all part of this bigger vision of creating a more open, more transparent, more collaborative research ecosystem.
Okay, so we've gone deep into the mechanics of Sigma. We've explored its facets, its contributions, its constraints. We even peeked into the potential for, sharing and reuse. This paper paints a pretty exciting picture of the future of economic research, but let's be realistic. It's not all sunshine and roses, right? What are some of the hurdles that Sigma might face along the way?
Well, one of the biggest challenges is going to be adoption. You know, getting economists to embrace a whole new way of working isn't going to be easy. It requires a shift in mindset, a willingness to learn new tools, and a commitment to sharing knowledge openly.
It's like convincing everyone to, switch from horses to cars.
Yeah.
There's bound to be some resistance from those who are comfortable with the old ways.
Exactly. Another challenge is complexity. Building a system as, sophisticated as Sigma is a massive undertaking. It requires meticulous design, rigorous testing, and, ongoing development to ensure it can meet those evolving needs of the research community.
And it's not just about the technology itself. It's about creating a system that's both, powerful and user-friendly, something that researchers will actually want to use. We also need to think about, governance. Who will oversee the development and, maintenance of Sigma? How do we ensure that the library of processors and constraints is, accurate, reliable, free from bias?
Right. Those are crucial questions. It's like, establishing a new form of currency. You need to build trust. You need to ensure the, system is stable,
Sure.
secure.
It's a tall order, but the potential rewards are huge. It's like we're on the verge of a paradigm shift in economic research.
Yeah.
Moving from a world of silos and secrecy to a world of shared understanding,
Yeah, no,
collaboration.
precisely. This paper, it's more than just a, technical proposal. It's a call to action for the economics community. It's about embracing a new way of thinking, a new way of working, a new way of, sharing knowledge.
It's about democratizing access to, powerful tools
Yeah.
and empowering researchers to tackle some of the biggest economic challenges facing, our world. This has been a mind-expanding deep dive, and I'm walking away with a whole new appreciation for the the potential of sigma. But the conversation doesn't end here. We encourage you to explore this paper further. Think critically about its implications, and maybe even consider how you might contribute to this exciting new frontier in economics.
Who knows? Maybe one day, thanks to systems like Stuxnet, we'll see a world where economic research is truly open, transparent, accessible to, everyone.
A world where collaboration, shared knowledge, they lead to better insights, more informed decisions. Until next time, on the Deep Dive.